Hi class, this is Sir Alex Basco, and today we are going to continue on in our lesson in lesson 3.2 for our General Chemistry 1. Last time, lesson 3.1, we discussed representing compounds by identifying some of the formulas, molecular formulas, empirical formulas, and we discussed about structural formulas as well as perspective drawings. In perspective drawings, we learn about this Valence stick model and the space filling model. Specifically, a little bit I mentioned about the structural formulas, wherein we have to understand what we call the Lewis dot structure or just Lewis structure. So for lesson 3.2, we're going to go the basics of Lewis dot structure. We are going to go back and discussing Lewis dot structure on our next quarter, the last quarter. So today we'll be sticking to the basics, okay? And this is necessary in order for you to understand how we create structural formulas of various compounds. So at the end of today's lesson, what I want everyone to be able to do is represent compounds using chemical formulas, structural formulas, and models. More specifically, the structural formula, because that's where the Lewis dot structure comes, or structural formula comes from Lewis dot structure. So let's begin by first understanding what are valence and bonding. You cannot draw Lewis dot structure or the chemicals structural formula without understanding what we call the valence and the importance of valence in bonding. When we talk about valence, there's kind of like two things that you want to remember. First is the valence shell. A valence shell refers to the outermost shell according to the Bohr's model of an atom. What do we mean by Bohr's model of an atom? Bohr's model of an atom is basically you have your neutrons in the middle. Maybe let's use the black color to identify different colors. So let's have the black color as our neutrons, and neutrons do not have any charges, they're positive. And then we have what we call protons. Let's use blue for protons for positive charges. Let's draw two. So we have two protons, and our neutrons and protons are basically in the middle. They are in the nucleus, right? So they are inside our atom. That's But according to the Bohr's model of an atom, the electron are actually outside, not basically outside, but they are kind of like not in the nucleus, and they are actually moving about. They're not stationary. They're going. It's a type of like a cloud. You can think of it as a cloud that keeps moving. So this is actually helium right here. This is helium, wherein it has two protons and two electrons. That's what makes helium. One thing that I want you guys to understand, the elements that we are dealing about, carbon, oxygen, blah, 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 are all atoms. The only difference that they have is the number of their protons, neutrons, and electrons. For example, if I remove these and that and retain one, and I remove this, I only have one proton and one electron. What I have is actually just hydrogen. This is a hydrogen. But if I increase the number of protons to two, oh, it's different color. But if I increase the number of protons in, sorry, to different color. There you go. If I increase the number of protons into two, and I added two neutrons, so two neutral charges of particles, and then I added another electron, this becomes a helium. So by adding and subtracting, basically much more adding, by adding the number of protons and electrons in an atom, you are basically creating various elements, various single elements. So that's what is actually the periodic table is. If you start looking at the periodic table, that's what it is. You're just increasing the number of protons and electron. So let's go back to valence shell. What is valence shell? Valence shell is this, you can imagine this as this ring right here. It is the outermost shell of an element. And depending on an element, they have various numbers of shells. So, for example, for hydrogen and helium, they only have one shell. And the first shell can accommodate two electrons. That's why we have two electrons here. So if I remove one electron and go back to the picture that I have earlier, what I have is hydrogen wherein there's only one electron in it in its outermost shell. Then aside from the first shell, if I have a second shell, the second and the succeeding shell, third, fourth shell, blah blah blah, can accommodate about 8 electrons. So when we talk about valence shell, it is the outermost layer. It is the last layer or the layer outside of our element. In this case, helium. This is the valence shell of an helium. And there's something called the valence electron. Valence electron is basically the electrons present in the outermost shell of an element. So we have something like here. Okay, so if you look at there, so we have about 1, 2, 3, 4, 5, 6. You have 6 protons and 6 neutrons, and then we have 6 electrons. So the valence electrons are basically the electrons present in the outermost shell of our element right here. So like I mentioned, the first shell right here can accommodate 2 electrons. But if I go to the second shell, the valence, this becomes the valence shell. This needs to have about 8 electrons. So right now it only has an 8 electron. So just these things to remember. I don't want to make it complicated, but valence shell is just the last shell of the electron, and the valence electron is the electrons present in the outermost shell. So why is this important in bonding? It's because of what we call the octet rule. Atoms are most stable or least reactive. When we say most stable, they do not react when their outermost shell is full. So what electron wants to have is they want to have a full set of electrons in their outermost shell. Like I said, the first shell wants to have 2 electrons. So if the first shell has 2 electrons, it is full, therefore it is stable. That's why helium is actually very stable because it only has one shell. It is its valence shell, and it already has 2 electrons. Therefore, helium is very stable and does not usually react. But the succeeding shell, the second shell, third shell, blah blah blah, until the last shell, whatever how many shells the atom has, the last shell is usually the valence. It wants to have about 8 electrons. So as you can see now, if I have this type of situation, look at this element right here. This element is actually carbon. This is carbon. It has 6 electrons and 6 protons. So, and in its outermost shell, it has 4 electrons. Like I mentioned, since this is already the second shell, what it wants to have is to have 8 electrons. But normally, and under normal condition, carbon only has 4 shell in its valence shell, or it only has 4 electrons in its valence shell. So where this bonding comes from? What In order for us to bond, for carbon to bond, it wants to stable itself by adding about 4 more electrons onto its valence shell. So how does it do that? It's basically the term covalent bonding. It's the sharing of electrons. It needs to find an element wherein that element can share its electron. So I will show you more later on, but let's understand it here first. So if you look at here, the dots right here, these red dots that you're seeing, are actually the electrons present in the outermost shell of an element. So we have group 1, group 2, group 3, 4, 5, 6, 7, and then our group 8. Everyone in group 1 has one shell in their electrons, or has one electrons in their outermost shell. So they have all one valence electron. Group 2 has two valence electron. Group 3 has three valence electron. Carbon here, which is right here, it has four electrons in its valence shell, and so on and so forth. This is how you identify how many number of valence electron an element has. So where does the octet rule, how does these elements perform octet rule? Which means they want to have 8 electrons in their outermost shell. Like I mentioned, we have what we call covalent bonding. Covalent bonding is basically the sharing of electron between elements. Now let's look at the various examples. So let's have our Codigo or our elements there. So let's start with CH4. How are we going to write the Lewis dot structure to create structural formula for CH4? What we want to do is first identify the valence electron of these elements. So we have C, and we know that our C has 4 electrons in its valence shell. When we are writing for electrons, what we want to do is we want to put it in a way where we create like sites. So think of these areas as sites. So the top area, the bottom area, the left and the right are the sites where you want to put your electrons. So you want to fill this first before adding more electrons onto that site. So we have one electron here, two second electron, third, and fourth. Next, we have H, and our H only has one valence electron. There you go. So how does Lewis structure, how does it help you understand the bonding of an element? So since we have 4 electrons, you can see right now where you're basically connecting the dots. So take your element with the most open number of areas that they could bond. For example, this one. So you have 4 here, and then you have the H, 2, 3, 4. And then what you want to do now is you want to connect these dots. And that's basically now the structural formula of CH4. So what are we talking about the octet rule? Octet rule tells us that the valence shell of electrons wants to have 8 electrons, right? It wants to have 8 electrons in its outermost shell. This can be fulfilled by what we call covalent bonding. This type of bonding is called a covalent bonding, wherein if we count 1, 2, 3, 4, 5, 6, 7, 8. As you can see, the carbon now has basically 8 electrons. So the electrons from hydrogen is being shared in order to fulfill the 8 octet rule that the carbon wants. So everything from 4 going to 7, they want to have their valence shell have about 8 electron. For 3, 2, and 1, the octet rule is not as much of a rule. They are kind of like weird in their own way. They're unique. They do not need to have 8 electrons in their outermost shell. But for carbon, for groups 4, 5, 6, and 7, they want to have 8 electrons in their valence shell. And that happens by basically sharing or counting the electrons that you connect in their valence. So what happens now is these electrons also exist in the valence of carbon, creating the octet rule. So the carbon is stable and the H is also stable because remember, it follows the duplet rule. So it just needs to, the hydrogen has only one ring, has only one valence, and in the first shell, it wants to have two electrons. So as you can see now, the two electrons here satisfies the valence of our uh, hydrogen. So you can also draw it this way: 1, 2, 3, 4, 5, 6, 7, 8, and then you have H here. And if you draw the rings, you can see that the valence shell of carbon has now 8 electrons, and the valence shell of hydrogen has 2 electrons, and they are satisfied. So methane is actually very stable. Now let's look at something like NH3. How are we going to draw NH3? So we have our N. What we want to do first is count all the valence electron that N has. Since nitrogen is in the fifth, it has uh, five electrons, valence electron. So what we're going to do is write everything one by one on each side. So we have 1, 2, 3, disappeared. So 1, 2, 3, 4. So after fulfilling all the sides, we can now add we can now add another one. So I'm going to write it here. So nitrogen, as you can see now, has 5 valence electron in its, or has 5 valence electron. What's interesting here is it only needs 3 more electrons, right? In order to satisfy the octet rule. So since I have H here, so I have 3H, I can place the H here, another H there, and there. And then I'm just going to basically connect this, creating a covalent bonding. So what happens now, this situation right there is called a lone pair. And this lone pair is actually stable on their own. It has a, it doesn't need to connect. Yeah, so but then if you count all the electrons that the nitrogen has, so 1, 2, 3, 4, 5, 6, 7, 8, the octet rule is satisfied. Therefore, NH3 is actually a very stable element. So that's how you kind of like write the Lewis dot structure. So identify how many electrons are in the valence of each element, and then choose the one with the highest number of electrons that can connect, and then surround it in around that element. Now let's look at some various example. Let's say C2H6. How am I going to write C2H6? So we know that C has 4, 3, 4. C also has 4. And then I have 6 electrons. So how am I going to write this? So first what we're going to do is let's connect the carbons together. So that's connected there. And then let's count how many more times that our carbons needs to connect. So 1, 2, 3, 4, 5, 6, and that matches. We have 6 electrons. So that's basically, they're all basically surrounding each 3 hydrogen for each carbon. So this is just the basics. It can actually get a little complicated, especially when we start counting for mole charges, but let's just keep basic for now. So this is C2H6. So this is the structural formula for C2H6. So far these are a little bit, easy. Let's try um, a little complicated. So let's try maybe something. Let's see, and carbon dioxide and carbon monoxide. Okay, so let's try this. So we know that our carbon has 4 valence electron. Our oxygen, since it's in the 6th group, it has 6. So to write that, you just want to do each side. So we have 1, 2, 3, 4. Now you can pair 2, 3. So this is our oxygen, and we have two of these. So how am I going to join these together? So since I have two, which electron has more, which of these elements wants to connect more? So carbon wants to connect 4 times, while oxygen just wants to connect twice. So we're gonna do carbon as our central atom. So let's have carbon, and then let's place one of our oxygen here. So that's one. And as you can see, these are lone pairs. These are stable on their own. They don't need to connect. And then we have another oxygen. We can put the oxygen here. There you go. Maybe let's move over here. Okay, so let's connect this one and let's connect this one. So are we done? Not yet, because as you can see, there's one more that the oxygen wants to connect. And so here, so the oxygens want to connect one more, and the carbon wants to connect again. So we can actually connect these together. So what we ended up having is something like this. There's a double bond for carbon dioxide. And, and we can count, since everything is above the fourth group, we can count if it fulfills the octet rule. So if we have this carbon, let's count 1, 2, 3, 4. So that's 4 electrons, 5, 6, 7, 8. So the carbon is satisfied with 8 electrons. How about the oxygen? So we have 1, 2, 3, 4, 5, 6, 7, 8. The same thing for our oxygen. The octet rule is satisfied. 1, 2, 3, 4, 5, 6, 7, 8, and our oxygen is also satisfied. So that's how we can connect if we have something like double bond. So this is the structural formula of carbon dioxide. How about carbon monoxide? Let's look at carbon monoxide. CO. So we have C, 1, 2, 3, 4, and then we have an O, 1, 2, 3, 4, 5, 6. And if you look at this, so we have 1, 2, 3, 4, or can do it this way. So we can connect that, and we can connect that. So C, O. So this could be your what do you call this? So you might think this is the correct way to combine them together, but as you can see, it's kind of like not balanced. So what will happen is actually the carbon dioxide now can donate one of its electron to the carbon, creating like a triple bond. So these two right here, so what we ended up having is something like this. And if you count the electrons that they have, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, the same thing, they have 10, 10. That's why this is actually carbon dioxide. They have 10 electrons each in their valence. It's very, very reactive. It doesn't want to stay on its own because it doesn't fulfill the sextet rule. There's too much energy going on for our carbon monoxide. But I hope you're getting how to write the Lewis-Strauss structure. Basically, what you want is to identify the valence shell of your element and then basically connect the dots, making sure that the element with the most number of electrons that it can connect, so that's basically the fourth column usually becomes the center atom, and then just surround the center atom until you find a way to connect everything thing. Okay, so that's basically the Lewis dot structure. So let's erase some of these examples, and I'm going to discuss something a little bit more about Lewis structure, called sigma bonds and pi bonds. Let's go back to our sample problem here. Let's have a CH4. We know that CH4 has this structure. This single bond right here are called sigma bonds. Pronounce this as sigma. So sigma bonds are basically single bonds, that's single line. But if we have two more bonds, for example, these are called pi bonds. So like the pi, like the ones in the circle, pi bonds. And then if we have three, this is also called a pi bond, the third bond. So if you have CO or carbon monoxide, what you have is you have one sigma bond and basically two pi bonds, because you have one and then you have double, that makes one pi bond, and then the triple becomes another pi bond. So you have one sigma bond and two pi bonds. So that's basically what we call when we are dealing with number of bonds in our Lewis structure. And lastly, before we finish up about Lewis structure, let's talk about formal charges. Some elements are unstable. For example, carbon nitrate, carbon and nitrogen. So we know that carbon has 4 and nitrogen has 5. So how are these going to react? So what happens is we can actually connect those three. So you have 1, 2, and 3. And as if you may notice here, it has an electron here that it wants to connect. So this is very reactive. So sometimes when you have carbon nitrate, what happens is you would see a negative sign. If you see a negative sign there, it means there's an addition of another electron. Remember, if there's negative, there's an addition or gain of electron. If this is positive, there's a loss of electron. So Cn negative means we want to have, or you want to add another electron. And that means typically you would have what we call, these are the polyatomic ions. They're covalently bonding, but they function as a single unit as an ion because we increase the typical number of electrons that the carbon has. So what happens is you basically have a carbon that has an extra electron, just in order to make this stable. And like mentioned, like carbon monoxide, this is also very reactive because it has more electrons than the valence in its valence shell. So this is this is where we get polyatomic ions. And polyatomic ions, we discussed that next in our lesson 3.3, just a little bit about polyatomic ions. Okay, so but if on our test, if we're going to, or if when we have a test for the Lewis structure, I'm gonna just remember this, and it's just gonna be basic Lewis structure, nothing really out of the normal. But this is something that I want you guys to remember. If we have single and triple bonds, those are pi bonds. Single bonds is just a single um, bond, this like the ones we have in CH4. So just do not forget how to do the Lewis structure. Again, we're going back to Lewis structure. This is just the basic of Lewis structure. I'm sorry if the explanation is not clear, but I hope you guys understand it. If you guys have any question, do not hesitate to message me. Thank you guys and have a great day.